Welcome back. We've talked about the Morzalve theorem. We've talked about the torsion subgroup. Now we have to start analyzing the free part or point of infinite order. The crucial problem here that we are going to face is how to identify which points are related. If I give you 2 points on an elliptic curve, 1, 2, and 17, 37, how do you know that these 2 points are not like a multiple of each other, for example? How do you know if you have 3 points? How do you know that one of them is not some linear combination, a z linear combination of the other 2? This is not just linear algebra where that is a trivial problem. Now, because the addition is so complicated, that a problem is complicated. So what we have to do is linearize. So we have to find a way to use the holy grail of mathematics, which is linear algebra, to compute those things, to be able to use linear algebra to compute whether things are linearly independent or not linearly dependent. But again, that is tricky when you're talking about Z modules, not just vector spaces. So we're going to use heights for that. So here, remember, let's recall that we have a few heights already defined. So we have a trivial height on Q. Our height was the height of a number, of a rational number, was just the max in lowest term. So P and Q are already relatively prime, is the max of the absolute values of the numerator and denominator. So it just gives you a size for a rational number. Then we defined a height on an elliptic curve by taking, well, the height of the x coordinate. But because it grows, the height grows exponentially with the multiples of a point, we take a log in there too, so it's not like fully out of control, that growth. So here is the log of h of x of p. So instead of exponential, now the growth when you multiply by p is not linear, but it's quadratic and in the multiple. That and O if not O. So the value is 0 if P is O. Okay, so we have those. Now, more generally, we can actually construct a height for any even function on E. So the thing that we're using here about the x coordinate is that the x coordinate is an even function. The x coordinate of P, in short value stress equation, at least, the coordinate of x, the coordinate x of P is the same as the coordinate x of minus P, right? So, and in long value stress equations, it's the same thing. The y coordinate is just not minus the y coordinate, but the x coordinate is the same. So f are actually the even functions on E. X is one of them, but you could pick in any other. So in general, if f is an even function on E, we define a height, which is just like before, is the log of the height of f of P. If P is not 0 and O, it's 0 if P is O. Okay, so the first thing that I'm not going to prove is that it turns out that this is also a height. Also a height. And remember that the definition of height was the 3 properties we needed for the descent theorem to work. Okay, that that the height of m times p is approximately m squared times the height of p, that the height of bounded sets or the size of bounded sets in height is finite, and then when you fix 1q and you add p, that is smaller than the height of 2p, regardless of what p you choose, essentially. Okay. All right. So so now two theorems about heights in general, which I'm not going to prove, but these are sort of like similar trickery like we did before for the properties of the height of the x coordinate. The following are true. So suppose that you have a function. This is the function field over Q of E, an even function. Remember, by the way, I didn't say, but the fact that it's even, it's just that f of p equals f of minus p. Then first, for all p and q on E, we have that the height of p plus q plus the height of p minus q equals twice the height of p plus twice the height of q plus a constant, which I'm going to call, this is O of 1. This is just a constant that depends only on E and F. Okay. By the way, this is what's called the, except for the constant, so if you forget about the constant, this is what's called the Parallelogram Law, and that is a property that quadratic forms satisfy. Okay, so what this is saying is, i.e., h of f is almost a quadratic form. And if it was a quadratic form, then we're almost there. So we're going to have to modify this function a little bit so that constant goes away. And second, if f and g are even functions, then what is the difference between one height and the other? It turns out that the degree of the function g times h of f is the same that the degree of f times h of g plus, again, a constant that only depends on E, F, and G. Or maybe this one only depends on E, actually. So that is sort of like the exchange rate between h of f and h of g. Right. Not going to prove this, but I'm going to use this to construct what we call the canonical height. So here is now proposition. Again, let E over Q be an elliptic curve, an even function on E, and let P be a rational point. Then the limit 1 over degree of f, limit as capital N goes to infinity of the f height of the 2 to the n multiple of p divided by 4 to the n exists, and it's independent of f. Great. So if you thought you were in number theory and you did not have to prove that sequences were Cauchy anymore, you were wrong. And what we have to first to prove that this limit exists, and then that is independent of f. So we're going to compute. We're going to first we're going to show that the sequence is Cauchy. Right. So from right A, there was no part A. So first we're going to show that the sequence is Cauchy to prove that there is a limit. For the property B of heights, okay, which said that, remember this says that HF of 2P is bigger or equal to 4 HF of P minus C2. Okay, so it's the property B of heights for M equals to 2. This implies that there is a constant such that for all Q, for all rational points, we have that the height of 2Q minus 4 times the height of Q is bounded by C. Okay, that C is like the C2 in the properties of heights. So that is universally bounded, the difference between 2Q and 4 times the height of Q. Great. So now let n bigger or equal to m bigger or equal to 0 be integers. And look at the property, the Cauchy property. So what I want is HF 2 to the n P minus or divided by 4 to the n minus the height of 2 to the m P divided by 4 to the m. I need that to be, well, I need that to be bounded, right? So I need to bound that somehow. All right, so what I'm going to do is I'm going to make a telescopic sum. So I'm going to add and subtract all the terms in between the nth term and the mth term. So I'm going to make them all appear just by adding and subtracting. So this is the sum for little n from m up to n minus 1 of the height of 2 to the n plus 1 p divided by 4 to the n plus 1 minus the height of 2 to the n p for n. Okay. Now, this is less or equal to use the triangle inequality to show that this is the sum. The sum comes out, and the absolute value is just going to be in the numerator. This is the absolute value of HF 2 to the n plus 1 p minus 4 HF 2 to the n p, like that. But now using Q, like in here, okay, for all Q, so use Q be 2 to the n p. Then using the universal boundedness, because it's a height, this tells me that this is less or equal to the sum from m up to n minus 1 of c over 4 to the n plus 1. And now this is a geometric sum. So just pull out the c constant as a common factor. Do the sum, and this is less or equal to c, if I did that correctly, 4 to the m. Okay. But then as m grows large, regardless of what n is, this goes to 0. So this goes to 0 as n m grow, with m going to infinity, and therefore it is Cauchy. And converges. Okay, so analysis over. All right, so how about this has to be also independent of the even function f that I chose. So let me show that it is the independence. For the independence, if g is another, if g is also even, then what I proved is that you remember that what I call the exchange rate between between f, oops, I had it right, that was supposed to be a g, and between f and g was just bounded by a constant. So if you divide by 4 to the n everywhere, then what I get is that the degree of g of hf 2 to the n p, so evaluate at 2 to the n p and divide by 4n, then I get this equation. So when I take the limit, this is going to go to oh yeah. Remember, so the key here is that what should I do? I should also divide. Actually, what I should do to get everything on the nose is that I should also divide everything by 1 over degree of g, degree of f, and then there's also going to be here 1 over degree g times degree f. This is still going to go to 0, and then when I get this, then this factor is going to go to the limit of 1 over degree f hf divided by 4n, and this factor is going to go to the limit of 1 over degree g hg divided by 4 to the n, and this is going to be 0. So the two limits coincide. They exist, and now that they exist, they actually coincide regardless of what even function I picked. Okay? So the limits coincide regardless of the even function that we picked. Okay? So that is, that's great. Whenever we have something like that, we make a definition for it. That is going to be what we call the canonical height. So the canonical, it has a name, the canonical neuron Tate height on EQ is h hat from EQ to R, given by the height is 1 over degree of f, limit as n goes to infinity of hf 2 to the n p over 4 to the n, and where f is an arbitrary even function. For example, the x-coordinate. By the way, note that the height of O, since 2 times O, 4 times O is always O, the numerator is stable, it's just 0, and therefore the limit is 0. So the height of O is 0, the canonical height. Okay, so this has a very nice property. Computing it is a completely different story, but computing it, the limit is actually not going to be too far from the naive f height of p. So it's about that, but then the limit, it just sort of adjusts a little bit the value. So it is going to satisfy really nice properties instead of approximately very nice properties. I think I only have 5 minutes, so let me just state the properties. So next time I can just start with the proofs. So let E over Q be an elliptic curve, and the canonical height is h hat. Then this is a theorem in Silverman, and I'm reordering things a little bit. So I'm going to start with part E. If f is even, then the degree of f times h hat is hf plus a constant that depends only on E and F. Okay, so that's what I said, that essentially the canonical height is just h of f divided by the degree of f, except up to a constant. So you are pretty close. Well, the constant could be huge, but in any case, you can sort of like find out what that constant is and just figure out how far you are from the actual canonical height. Now, more importantly, for all P and Q on E, we have the parallelogram law. The height of P plus Q minus the height of P minus Q is twice the height of P plus twice the height of Q, which is again called the parallelogram law. Okay, and that tells me that h hat is going to be a quadratic form. B, for all P in Q, now this I hope you appreciate immediately, is that the height of M times P equals M squared the height of P on the nose. No constants. Okay, that immediately, if I tell you the height of P12 is 3, the height of 3713 is 5, then immediately you know that they are not multiples of each other. So they have to be independent as points. They cannot be, one is not the multiple of each other. So so that's nice. Okay, so that's the kind of thing that we're going to use. And more impressively, h hat is a quadratic form on E, i.e. h hat is even, and the pairing that you get from E cross E to R given by PQ goes to the pair A PQ, which is height of P plus Q minus height of P minus height of Q is bilinear. All right, and the height, the canonical height, can tell apart torsion points. So the height is always positive, the canonical height, and the height is 0 if and only if the height or the point is torsion. Okay, I really like that one. Finally, if h hat prime satisfies some other function, some other height that satisfies E and B for any m bigger or equal to 2, then the canonical height is canonical. Okay, so that is what explains that if you have that height that satisfies E and B, then it is actually the canonical height that we've already described. So that is why it's canonical. Okay, so I'm going to stop here. We're going to prove these properties, and then out of these properties, we're going to analyze, construct something to be able to tell when points are linearly independent over the integers. Right, very good. So I'll see you next time.